Welcome to the APL Quest. See APL Wiki for details. This is the first problem of the 2014 set from the APL problem solving competition. We're given as left argument the two supposed shorter sides of a triangle, and as right argument the longer side. We are to check if these three numbers together can work as lengths of a right-sided triangle, a right-angled triangle. It's of course natural to use the Pythagorean Theorem. Let's put in some test cases here. Two shorter sides 2 and 4, another case with shorter sides 3 and 4. We're going to try this with a longer side, that's 4.5 and 5. The first one is going to be false, and the second one is going to be true. The Pythagorean Theorem states that the sum of the squares of the left of these two shorter sides matches the square of the longer side. We can write this in various ways. If we observe that the square is the same thing as multiplication by itself, then we can see that we are summing over the application of a scalar function. A scalar reduction over the application of a scalar function application is the same thing as an inner product. And here we have the same argument being used twice on the inner product, which means we can use the selfie or commute operator. We can do the same thing with commute for the multiplication. Just a different way of stating the same thing. We can also make it tacit. We want this inner product applied on the left argument, and we want the self multiplication applied on the right argument. Same thing, just in a tacit form. We can also break out the multiplication because we really start with squaring both arguments and then we're summing one of them. So by using the over operator, we can pre-process both arguments with self-multiplication or squaring. And now we only need to sum the left argument. So we could write this as the sum of the left argument matches the right argument. Or we could use normal equality but pre-process an argument. We can't pre-process the left one, but we can pre-process the right one. And we're going to pre-process it with summation. The problem is, of course, it's the left argument we want to deal with. But we can fix this by commuting, swapping around the two arguments. We could also start off by commuting. Then we pre-process with squaring. And then we have the summation on the right. However, observe that a reduction over a single element doesn't actually change it. So the fact that we're pre-processing only the right argument with the summation, we can use that to fold this reduction into our pre-processing of both arguments, because a summation of a single argument doesn't matter. Here we have equality, where we pre-process both arguments with the summation of the square. We don't need to commute anymore, because we're treating both arguments exactly the same. And of course, we can combine this plus reduction over the multiplication into an inner product, if we prefer that style. A whole different way to approach this is by using complex numbers. So in the complex plane, we can look at the two shorter sides as the two components, the real and the imaginary, and then we have the diagonal being the magnitude, the whole length of that vector in the 2D space that the complex plane forms. So now we just need to combine these two parts into a single complex number. And it doesn't matter which one becomes the real part and which one becomes the imaginary part, because we're going to take the absolute value of it anyway. So we can start off by saying the last element of the left argument, we multiply that by the imaginary unit, and then we take the first element there and add to that. So this combines the two. Now we can take the absolute value of that and compare it to the right argument. We can also make this tacit. All this thing that we're doing is really pre-processing the left argument. So as before, we can swap our arguments around and pre-process the right argument instead. The last element, we multiply it here, and then the first element, take the absolute value of that, and that's how we pre-process. Another way that we can write this is using negative 11 circle. That's simply its definition. It just multiplied by the imaginary unit. Then someone came up with a clever thing using 4 circle. If we apply 4 circle, and we get back to what exactly that means, on the ratio between the two elements in the left argument, and then we multiply by the second element, then that should match the right argument. And that holds for our test cases. Let's prove that that is in fact the case. For that, let's try to make a tacit. Again, we're pre-processing the right argument, so we can write it the ratio of these two, the 4 circle on that, and then we just want the last argument, the last element of the original left argument. So we can write that we can either combine these two, take the first of the reverse, but we can also just use a right-tech reduction, it's a right reduction, and we pre-process the right argument to the equality with that, and we just need to commute things around. So this is the tacit form of that. Alternatively, we could use first, and we could commute the elements of commute the arguments of the division, and that would also work. But how does it actually? How does this actually work? Let's go back to our definite form with let's see, with 4 circle right here, this one. So the definition of 4 circle is the square root, which we don't have in this APL, but we're using this as a placeholder. We're going to eliminate it later. So the square root of 1 plus the square. This is going to be a little bit complicated using the elements of the left argument. So let's give them names, A and B. Now this is the last one is B, and the fraction formed by them is just A divided by B. Here's the square of a fraction. That's the same thing as the fraction of the two squares. We have a B outside the square root. We can get it into the square root by squaring it. Now we have 1 plus this fraction, where the denominator is b squared. That means that we can add on top of the fraction b squared instead. And now we can observe that this whole thing, this sum, is being divided by b squared, and then it's being multiplied by b squared. Those eliminate each other. We have a square root here, and we can just square on both sides of the equality. And now we have the sum of squares here, so we don't really need these names anymore. It's just the sums of ab squared And a and b together, they are the left argument, so we can get rid of our temporary names. And this is exactly the Pythagorean theorem. So we've proven that the solution using 4-circle is exactly the same thing. Okay, now for the last solution, which is a bit involved, and it uses the rarely used domino function, which is matrix inversion, although we're using it here only on vectors and scalars, so it's a bit of a misnomer to call it matrix inversion, maybe vector inversion or just inversion. And it's very clever. It is the ratio between the inversions of both arguments. So this is using over. We check if it matches the ratio between the arguments. Okay, what's going on here? How does this work? It does actually work for our test cases, but let's start to unpack this a bit. And so first we have a division here, and we're preprocessing both arguments using this domino. Here's the right argument, and here is the left argument. And then we are checking if it matches the ratio between the arguments overall. Now, this inversion function, when applied to a scalar, is exactly the same thing as just a normal reciprocal. So we can replace that. And we can also see that we're dividing by a reciprocal. That's the same thing as a multiplication. So far, so good. What does it actually mean to invert a vector? What it does is it finds a vector for which the dot product with the original vector gives 1. So it's, in a sense, it's inverse. Just like 5 and a fifth multiplying by each other, you get 1. So the vector is going to have the same direction, but the reciprocal magnitude. This is this means that the inverse vector would need to be multiplied twice by the magnitude to get the original vector. Right? Since multiplication once by the magnitude gets us to the middle to 1. So that's the same thing. That means that multiplying twice by the magnitude gets us all the way back to the original. Let's test this out a bit. So we invert 3 and the 3, 4, and then we can multiply that twice by that supposed magnitude, and we can see that we're right back where we started. If we try to do this for arguments that are not forming a right angle triangle, then we're going to see that it's not going to work to add up. Close, but not quite. Nope, this isn't even right. It's supposed to be 2, even closer. Still not right. Have our example from before. So if multiplying it twice gets us all the way there, multiplying it once gets us halfway there, kind of meeting in the middle. Where do we? So if multiplying the inverse by the magnitude twice gets us all the way to the original argument. If you only multiply it halfway there, only multiply it once, then it would be the same thing as starting from above, starting from the original and dividing it once by the magnitude. Hence, what we have here. So we multiply. So this is the diagonal, or the magnitude, and we're multiplying it once by the magnitude is the same thing as dividing the original by the magnitude, and that only holds if it's a right angled triangle. So we need to test if they meet in the middle. If the inverted vector times the supposed magnitude matches the original divided by the supposed magnitude. Then they met in the middle, and then what we've supposed is the magnitude is actually the true magnitude. Okay, so we said that the inversion of this vector is the same thing as scaling it down twice by its magnitude. So let's test that. Let's write that out. So we're scaling it down, we're dividing it by its magnitude twice. And its magnitude is, of course, the square root of the squares of its components. Next up, we see that we have a square root here, but it's squared. So they cancel each other out. Oh, sorry, let's go back a step. We had the square root of the sum of the squares, of course, to get the diagonal, and that was being squared. Yeah, so these two cancel each other out, and we have the sum of the squares that we are dividing the original by. Now we can see that we have alpha divided by something over here, and then multiplied by something. And over here we also have alpha divided by. So if you divide both sides of the equality by alpha, we can eliminate that. Now we have the reciprocal of this times the right argument. So a reciprocal multiplied by something, that's the same thing as that something divided by the value. Then we can take we have a reciprocal of the right argument over here, and let's take the reciprocal of both sides of the equality. That eliminates this, and we just need to swap over the arguments over here. We divide by the right argument over here, and here we just have the right argument. So let's multiply on both sides of the equality by the right argument. That eliminates this division. And this self-multiplication is, of course, the right argument squared. And therefore, we have here the Pythagorean theorem again. The square of the long side equals the sum of the squares of the two shorter sides. So that's how this very impressive 5-character solution works, and it's in fact the exact same thing, but just in a very disguised way. And then with one caveat: since we're doing all these divisions, if we have any zeros, then it will fail. So it doesn't actually work if sides are 0, but other than that, it's very clever. Thank you for watching.